normally use Bayesian theorem to condition the later on the former, okay, to condition the unknown on the known, okay, in other words, to condition, well, I think, last chapter we already talked about this a lot, so I will not. If you write the formula, we know that. Very well. I just erase it. I kind of feel like I shouldn't erase it actually. Anyway, okay. So generally, we refer to the knowns as data, okay, treated like a constant, okay. The unknown as parameters of your model actually, okay, and treat them as probability distributions. Okay, so the Bayesian inference or Bayesian data analysis is to eventually obtain the distribution, okay, posterior distribution of these parameters, okay, conditioned on the known, okay, which is conditioned on the data, okay. So in more formal terms, we assign probability distribution to unknowns quantities. Then we use Bayesian theorem to transform the prior probability of probability distribution into posterior distribution. We have talked about this. Several lectures already. Okay, so here users specify a full probabilistic model by writing a few lines of code. Okay, and then inference follows automatically. Okay, this automatically is an important thing, okay? Of course, okay, you can control this inference, many options of this inference, by yourself, but you will be surprised to find that, okay, the modern Bayesian inference package such as PyMC3 or for example, like some package under the R, okay, they are able to do this inference automatically, and the result is already good enough, okay. So I will show you, through example later anyway. So this will enable practitioners, okay, the people like us, to build complex probabilistic models in less time-consuming, less error-prone way, because, well, you don't need to play with the parameters, you don't need to play with those options. Basically, the package already can already decide them for you automatically. Okay, so the probabilistic programming language, this impact on data science is like a fortune programming on scientific computing. I don't know, maybe nowadays nobody knows fortunes anymore, right? Anyone knows fortune in this room? You nod your head. You know fortune? Yeah, we know the term, but has anyone in this room have ever written a fortune program? I don't think so. But back to to be honest, even when I was a student, fortune is already outdated. Okay, when I was a student in computer science, because when I was a student in mathematics, my undergraduate degree is in mathematics from 1987 to 1991. At that time, I think fortune was still popular. But after I went to US to study computer science, that was 1993. Nobody used fortune anymore. Okay, at that time, people are talking about C. Okay, and I think Java was newly invented at that time. Okay, and people talk about OOP a lot. Okay, so think about this. Okay, so Fortran was actually very, very popular, like back to like 1980s, okay, 1980s and early 1990s, okay. Without Fortran, to be honest, like we don't have the you know, we know like the U.S. sent the astronauts to moon, right? So I mean, in that mission, okay, all the codes were written in Fortran. Okay, so it was, but because nowadays nobody knows like after a couple of years, like 1990s, nobody knows like Fortran anymore, right? So it becomes so difficult for like the NASA to maintain those like old system, so they have to rewrite everything, but you can see like how important Fortran was like in the old days. But so Fortran has a big impact on like scientific computing. But unfortunately, you guys didn't know. But I just want to emphasize probabilistic programming. Okay, not necessarily PyMC3. Okay, because as I said, there are like other probabilistic programming libraries out there, okay, in R, okay, and to be honest, because like in this field, actually, like more people use R, and it's like or like Winbox, okay. There's like also some package under like Windows, okay. More people use those like package than the PyMC3, to be honest, okay. But this is the only one I can find, okay, that is supported by Python anyway, okay. So anyway, a probabilistic programming language, this is PPL, hides the detail on how probability are manipulated, how the inference is performed from user, allowing users to focus on model specification and the analysis of results. So how this analysis, how this inference is done, okay, I will not discuss that aspect in this chapter. I'm going to just talk about how you can do this inference through programming, okay, and the inside mechanism, how this is done. Okay, remember I told you like the NCMC, right? The Monte Carlo, like Markov chain Monte Carlo, okay, the sampling technique. I told you that is very important in Bayesian inference. Okay, but I will not talk about that this chapter. Okay, in this chapter I will only talk about programming. Okay, that part will be discussed like later. Okay, I will talk about that, but not right now. I want you to understand how to do the probabilistic programming first, and then you are able to play with that, which will be, well, part of the questions that I asked in the homework too, by the way. Okay. So for PyMC3, okay, what is it? Okay, it's a Python library for probabilistic programming. Okay, and its base code is written using Python, and the computationally demanding parts are written using NumPy and Theno. Okay, NumPy, you guys know, is part of like a Python, like a computational library, and Theno is actually a library for deep learning. Okay, and to be honest, Theno is now discontinued. Okay, the support for deep learning. It's because like in deep learning, everybody use like PyTorch or like TensorFlow or like Keras. Nobody use Thenos anymore. Okay, maybe because like we don't like the end game, right? Just kidding. But Theno, this Python library is no longer that popular. Okay, but PyMC3 is based on Theno. Okay, So no, this Theno allowed us to define, optimize, and evaluate mathematical expressions involving multidimensional arrays. Okay, because in deep learning we deal with those things all the time. Okay, so that is why Theno is very good at this type of tasks. Okay, which happen to be also very important in probabilistic programming. Okay, so well, the reasons for PyMC3 use Theno. Okay, some of the sampling methods, such as no U-term sampler. Okay, abbreviated as NUTS. Okay, this is one of the advanced sampling techniques. Okay, and is any sampling technique or advanced sampling technique are one of the MCMC methods. Okay, but let's just for now just remember this NUTS is one of the sampler. Okay, you don't need to worry about how this is done. Okay, we will talk about this later. Okay, I mean the concept and everything in more detail. Okay, so this computation, okay, need gradients to be computed. Okay, if you are into deep learning a little bit, you will know computing gradient is actually essential part of deep learning. Okay, in model training. Okay, so Theno know how to compute gradients using the automatic differentiation. Okay, so yeah, I will not go into a detail about automatic differentiation. Well, because I'm also teaching deep learning, so if you are interested in knowing more detail about, how this deep learning package compute the gradients, yeah, feel free to take my class next semester. Okay, so Theno compile Python code to C code, so that is also makes the PyMC3 efficient. Okay, it can be run very fast. Okay, so as a first example, let's see how we can write a program for the PyMC3 program for coin flipping. Okay, so for coin flip, we have tried to consider it using a grid approach, right? We have tried to consider this problem using the conjugate prior, right? So this is the third time we consider the exact same problem. Okay? So now, okay, first we set a random seed. Trials equal to 4. So theta real is 0.35. This is the real theta value, which is unknown, okay, which is supposed to be unknown, okay, but we define it here so that we can generate the data based on this real theta value and see if analysis result match this real theta well enough or not. Okay, so data equal to stats, Bernoulli, okay, RVS, okay, so so we use this theta value 0.35 and the trial to generate the data, okay, which consists of several flipping result. Okay, it could be 0, 1, okay, 4 of them. Okay, by the way. So for the likelihood, we'll use the binary distribution, okay, with n equal to 1, the p equal to theta. For the prior beta distribution with the parameters 1, 1. So 1, 1, if you remember, this is a beta distribution. So if you remember that when you assign A and B both to be 1, okay, it is flat, right? It's a uniform distribution, okay? So it looks like this. Remember, we talked about this not only this one, but also we use a figure. You remember, I told you that's Krusk, a diagram. Okay, in the last chapter actually, okay? So how do we write a program for this model? It's simpler than you think, okay? So with PM.model as our first model, so here, okay, we create this first model, okay, and we specify theta, okay, which is drawn from the distribution beta, and that theta just is a name of this distribution, and alpha equal to 1, beta equal to 1. Okay, that's very, so theta is drawn from this probability distribution. And then when you have the theta, okay, and you assign the p equal to theta, and well, that's the y is the data, okay. Observed equal to data. Remember, we generate those 4 trials. We feed that into this Bernoulli. Okay, Bernoulli is our likelihood, right? Okay, and this is our y. And then, okay, here, we sample, we do this, we call the PM.sample, okay, for 1,000 times, okay, with a given random seed. Okay, you can change the random seed, okay, if you want different sample, by the way, okay, and we will store all the result in the trace. Okay, this is an object, okay. Yeah, I mean, the following basically, I mean, yeah, I think I will not go into every single line. I mean, basically, I already told you like this program, okay? So if you want, I mean the explanation, like, you know, in more detail, you can check out like the slide, okay? So the last line, okay, is the inference button. So you can see that, okay, this PM.sample, we didn't specify a lot of information, but you know, this sampling process, okay, this sampling process is going to generate the posterior distribution for you, okay, automatically, without the need for you to set up like a lot of options. No. I mean, it will just generate this, you know, this inference button. So once you have that, okay, so it means we are asking for 1,000 samples from the posterior, and we will store them in the trace object, okay? So if you run the code, it looks something like that. Okay, so for this, you know, you see the first line, auto assigning not sampler. This is done automatically. Keep in mind, there are a lot of different samplers out there, okay? Of course, they are all MCMC variations, okay? NUTS is just one of the efficient MCMC samplers, okay? There are others, okay? To be honest, like different Python, different Bayesian data analysis textbook talk about different samplers, but they all based on MCMC. Okay, so so it automatically find the efficient sampler for you, and it will initialize NUTS using jitter plus adapt. These are like some options that will set automatically for you. You don't even need to set up this. Of course, you can set up your own options, but you don't have to. I mean, the program will. You know, this library will do it automatically for you, okay? And then multi-process sampling, okay, it will find out, okay, you have 2 chains in 2 jobs, okay? So what does that mean, okay? Because, I mean, nowadays all the CPU comes with multi-processors, right? Okay, so it will automatically find like several processors, several available processors in your computer, and have each process to run 1 chain. Okay, so this basically means that the program is getting the access to 2 cores in your CPU and run these 2 chains, in parallel, okay, for you, automatically, okay? And, so nuts theta. This just means like, okay, that's the posterior that we are collecting, okay, because we call this theta, right? The posterior is theta. So I mean, you notice that, okay, it's the posterior is for the theta parameter, okay? And then, okay, so you will see this bar running from 0% to 100%. Okay, so, well, it's actually, it should be very, very fast. Okay, nowadays the computer is, I mean, CPU is quick, right? But one thing you may wonder is that it says 3,000 over 3,000. What does that mean? It means that the inference, okay, this sampling actually collect 3,000 samples for you. But you may wonder, wait. I mean, previously we already said like we want 1,000 samples, right? And because we have two chains, so each chain we have 1,000, so it should have been 2,000, right? So how come it's 3,000? Okay, this is like, remember like I told you, like the program, the library will automatically find the good option to set up for you, right? But in order to find those good settings, it has to, collect certain number of samples to see if this sampling process is efficient. Okay, so actually, okay, for each chain, it is going to generate like the first 500 samples as a mean to verify, okay, to check if like I mean what type of setting is the best for the current problem. Okay, so each chain you have, but after that, okay, let those like 500 samples, okay, initial samples at the beginning will be discarded. So yeah, for each chain, it is going to generate 500 for certain parameter tuning purpose, and discard it, and then the next 1,000, okay, for the real analysis, for the purpose of analysis. So for each chain we have that. So two of them, so which makes like the total of 3,000 samples. Okay. So the number of chains depend on number of processes in your machine. So if you find out that, wait a moment, so it is running like six chains on your machine. Well, it may just because your CPU is more powerful, Yeah, it depends on the type of your CPU. So of course, okay, if that's 6 chain, then how many samples will be collected? It's actually not 6,000, right? It's 1,500 times 6, 9,000. Okay, 9,000. Okay, so I will skip this. I already explained this already for you. Okay, and then you can use plot trace. Okay, and in the plot trace, you just feed the trace that you obtain in here. You just feed this trace to the plot trace like function from RVs. Okay, and it will automatically plot. It will automatically plot these two figures for you. Okay, the first one is a kernel is a kernel function. Okay, you can consider this as like a, you know, a smoothed histogram for the distribution of the theta. Okay, and the right hand side actually indicates the, you know, the value for each sample. Okay, and obviously because we have two chains, right? So you can see there are two lines. Okay, one blue line and one orange line. Okay, and the same thing, we have two chains on the right hand side. Okay, on this right hand side, actually, okay, the x-axis of course represent the number of samples, but the y-axis represent the value of theta, and you can see like the theta value, you know, jump around, right, from top, you know, this is reasonable. I mean, of course, I cannot explain too much what this is until at a later time. Okay, after I explain the concept of MCMC, then you will understand more about that. But at least you can understand the left-hand side, right? That's pretty much the posterior distribution that we obtained from these two chains. Okay, and then you can also you know, obtain the numerical summary of trace. Okay, by the RVs. Okay, so so it will give you the mean standard deviation. I mean, MC error. I mean, at this moment, forget about this. I mean, this is related to MCMC. Okay, and this HPD 3%, HPD 97% means like the range from of like 94% HPD. I'm sorry, 94% HPD, the range of 94% HPD. Okay, from 0.02 to 0.64. Okay, and this efficient number and I mean, for these two things, don't worry about them. Okay, for now, because again they are related to MCMC. Okay, so they are related to diagnosing samples. I mean, so how is this chain? Are these two chains representative? Okay, those are something we need to consider in the MCMC sampling. Okay, but for now, you can ignore that. Okay, for now. Okay, so by default, plot posterior will show a histogram of for the discrete values and the KD for continuous variables. So so you can just draw this posterior distribution by using this function, okay, which will give you, you know, based on the generated the two chains that you generated. Okay, this is like we just call AZ. Okay, obvious. AZ is based on RVs, right? AZ dot plot posterior, and you feed the trace into this function. It will draw a kernel function for you. Okay. Because theta is a continuous value, so you draw a kernel function. If it's theta, if the sample are discrete, it will generate a histogram for you. Okay, automatically. Okay, so you will also indicate the 94% HPD range as well as your mean automatically. So you can see it's actually very simple to write a program to generate the posterior, right? Okay, I really highly recommend you to try it yourself. Okay, first, of course, you need to install like a necessary package, like for PyMC3 and the RVs, and then you can try out these programs. Okay, should be very easy. Okay, so we need to, but after we get the posterior, I mean, we need to, a lot of time we need to make decisions based on our inferences, based on our analysis result. The analysis result is a posterior distribution, but we need to, some decisions that we want to make are, dichotomous. Okay, for example, dichotomous means like a yes no question. That's the question we need to answer. Okay, but the result, I mean, that we have in this slide is continuous, right? So, for example, like health, sick, contaminated, safe, something like those. Okay, so one of the question may be like we want to decide if the coin is fair or not. Okay, remember, like we are talking about coin flipping. Of course, I mean, coin flipping can be used to represent many questions that I mean, for example, like is health, sick, contaminated, safe. Okay, all dichotomous like questions can be modeled by coin flipping anyway. Okay, so come back to coin flipping. Okay, if you want to decide if the coin is fair or not, what do we do? Okay, one way to do it is we compare the value of 0.5 against the HPD interval. Okay, so the HPD interval is from 0.02 to 0. It should be actually it should be 0.02 to 0.64. Okay, and yeah, this looks more like 64. Okay, yeah. So there's something wrong with this this value. Okay, it should be from 0.02 to 0.64. So 0.5. Okay, that value is included in this HPD. Okay, so if that's the case, okay, we could say that, okay, we cannot completely rule out the possibility that the coin is fair. Even though we know, okay, from this figure, obviously, it's the distribution is biased toward the tail, right? It's biased toward the tail. But, because the 94% HPD include 0.5. So we cannot rule out the probability, the possibility that the coin is fair. Okay, this is one way to determine, to make your decision. Okay, dichotomous decision. Okay, based on this posterior distribution. Okay, and if we want a sharper decision, we will need to collect more data to reduce the spread of the posterior. Okay, or maybe we need to find out how to define a more informative prior, because the prior that we use is flat prior. Remember, if we have a more informative prior, then the result may be more accurate. Okay, or if you are able to collect more data, because for this result, it is only obtained through 4 trials, right? 4 trials. Say if you are able to collect like maybe 10 or even 20 trials, you can imagine that this distribution will be more, what should I say, like it will be more narrow, and it will be taller, right? The figure will look like that, and obviously the 94% HPD will be also narrower, okay, which may not include 0.5. Okay, so this is one way to make a decision from the posterior distribution. Okay, so another way to make decision using the posterior distribution is what we call region of practical equivalence. Okay, which is happen to be abbreviated into an interesting term called ROPE. Okay, ROPE. So this ROPE is like a concept that has been used in Bayesian data analysis very often. Okay, so what is this? Okay, we generally do not care about the exact results, but the results within a certain interval. Okay, so we call this interval region of practical equivalence. Okay, so for example, okay, take the fair coin as an example. Okay, previously I say, okay, the fair coin has to be the theta has to be 0.5, right? But in practice, do we really think, okay, the coin, the theta value for the coin has to be exact 0.5 to be fair? How about 0.5, 0.00001? It's already close enough to a fair coin, right? Or it could be like a 0.49998. Okay, so do you consider those coins fair enough? In practice, those coins may already be considered fair enough, right? Okay, so for example, okay, we could say that any value in the interval 0.45 to 0.55 within this range, if the theta is within this range, then, okay, the coin is considered fair. So in this scenario, okay, the ROPE that we are talking about is this interval. Okay, that is why, okay, because in this interval we consider the result is predically equivalent. Okay, predically equivalent. Okay, so that's why it's called the region of predical equivalence. Okay. So once the ROPE is defined, we compare this ROPE against the HPD. Okay. So obviously, because you are comparing an interval with another interval, right? So there are 3 possible cases. It's no longer just 2 cases. Okay, because it's no longer a point consideration. Okay, so the first case is the ROPE does not overlap with HPD, or it's completely outside of HPD. If that's the case, okay, remember this ROPE, okay, 0.45 to 0.55 is the range, is the region that we consider coins fair, right? But if this region is completely outside of the normally 94% HPD, okay, then we can say that the coin is not fair with a more definite answer. We can say coin is not fair. So if another case is the ROPE contains entirely inside the HPD, then we can say the coin is fair. Okay? So for these 2 cases, I mean, they are easy to judge, right? The third case is there are partial overlaps between the ROPE and the HPD. If that's the case, okay, we cannot say the coin is fair or not. Okay, it's undetermined. It's undetermined. So compared this one with the previous, like a single point, like estimate, okay, what's the difference? Okay, first, this one is only, like, if the point is inside the HPD, we say, if the point is outside of HPD, we will say it's not fair, right? If point is inside HPD, we say it's probably fair, right? Probably fair. But first, like this exact 0.5 requirement for fair coin is really not practical, okay? Because pretty much, I mean, if you define like that, I mean, probably no coin match that fairness requirement anyway, right? Because we are talking about a fixed value in a continuous range, right? You know, like in a continuous range, I mean, talking about one particular value doesn't make much sense anyway, right? Normally, for a continuous region, we normally talk about a range instead of one single point, okay? And the second thing is like a rope approach gives us like more information. For example, we can say it's fair, it's not fair, or it's undetermined. Okay, so this is like if you know the confidence interval, okay, you will see that this actually has something to do with it's similar to confidence interval, but in the confidence interval, okay, there are some assumptions hidden behind the confidence interval computation. It's just like when you do the computation, you don't know those hidden assumptions. And those hidden assumptions really are not that reasonable, okay? In other Bayesian data analysis textbook, it talks about like why classical or like a frequentist approach, such as like a confidence interval, okay? Why those concepts are not a good idea, okay? But here, I mean, in this textbook, we don't talk about that much. But the confidence interval, I mean, or like NHST is used, okay, to make decision, okay, in traditional statistics. But here, okay, you can see in Bayesian data analysis, we use posterior and some very simple way to make a decision from the posterior, okay. It's much easier to make a decision, okay, based on posterior, okay. And this simple method, such as rope, okay, it doesn't have much additional assumption, okay, so which is nice, okay, compared with like NHST, okay, yeah. But if you don't know NHST, maybe, yeah, forget about what I'm saying. I was talking about. But if you know NHST, maybe I can tell you some additional material to study. Okay, but anyway. So, of course, rope is interval, right? So how do we choose appropriate rope? Okay, this is like based on background knowledge. Okay, any value inside this interval is assumed to be of practical equivalence. Okay, so you could choose, the fair coin to be in between 0.45 to 0.55, or you can choose rope for coin fairness to be in the interval 0.1. If you do that, well, no matter how you collect, how you do the analysis, the coin must be fair, right? Because that's the possible range for the theta value anyway, right? Okay, but this is trivial, unreasonable, and a dishonest choice, and probably nobody is going to agree with that, right? So basically the choice of the rope should be, reasonable and honest choice based on your background knowledge, and which can be recognized by the majority of the people. Okay? So, so we mentioned this unreasonable, region, okay? It's just to highlight the fact that the definition of the rope is context dependent, okay? So it depends on the problem. There's no auto magic rule that will fit everyone's intentions. Decisions are inherently subjective, and our mission is to take the most informed possible decisions according to our goals. So basically, you have to, based on the background, find the most suitable rope. Okay, so that's based on your subjective knowledge, background knowledge. Yeah, but at least, if you, this 0-1 rope is obviously, absurd setting. Okay, but you can set it to be, say, 0.4 to 0.6. That's also reasonable, right? Okay, or if you think like, okay, you have more demands for a fair coin, you can set it to be like maybe 0.48 to 0.52, something like that. And you see, basically it's a symmetric one, right? The setting should be symmetric, which reflects like, the symmetric nature of this question that coin is fair, right? So again, this, of course, even though we didn't say that, but you can clearly see that the rope, a more reasonable rope is a symmetric one, centered at 0.5. Okay? So you can use a plot posterior function to plot posterior against the rope. Okay? You just need to, set the rope, range, okay, when you use a plot posterior function, and it will demonstrate the rope by using this green interval. Okay, and it will also like tell you. From here, you can obviously see that. Okay, this rope, okay, is completely inside 94% HPD, right? So, which tells you that under such a rope setting, okay, based on the data that we collected, okay, this coin is fair, right? Because the rope is completely inside the 94% HPD. Okay, well, it's let's take 10 minutes break. Okay, shall we? Oh, by the way, for today, I have to probably leave like maybe 5 minutes earlier because I have a meeting at another building, like at 12 o'clock, which I cannot be late. Okay, sorry about that. But well, let's take a shorter break, maybe like 5 minutes, if that's okay with you guys. Okay. 可以吗? Okay. Yeah, sorry, it takes a little bit longer. I actually went to the department office for some issues. Okay. So I already explained like how you can set up the rope, okay, in the visualized like a diagram, okay, and you can also set a reference value, okay, in your posterior distribution, okay. Just need to when you use a plot posterior, just set a ref VAL, okay, to be, I mean, in this case, 0.5, and it looks like this. Okay, not only it will tell you, okay, it will mark this particular point. It will also tell you, okay, how much percentage of the data is below this point, and how much percentage of data is above this point. Okay, so this gives you a lot of information, on this reference value. Okay, so okay, then we can talk about these loss functions. Okay, the loss function is kind of, but not exactly, like the loss function that we use in like deep learning. Okay, in the deep learning, we train the model based on a particular loss function. Okay, but for Bayesian analysis, it's slightly different. Okay, because there's no training involved. Okay, the only thing that's like happen in Bayesian data analysis is like a sampling process. Okay, you are generating a lot of samples from a particular from some distribution. Okay, so make a good decision. It's important to have the highest possible level of precision for estimating the value, okay, of the relevant parameters. Okay, but it's also important to take into account the cost of making a mistake. Okay, so the cost or benefit trade-off, but can be formalized by a loss function. Okay, so this loss function sometimes is also called a cost function, objective function, fitness function, or utility function. I mean, whatever you call it. Okay, actually, I mean it's almost, these names are almost identical to the names used in deep learning, but I just have to remind you. Okay, they are different. Okay, their purpose are similar, but the usage of this function is very different. Okay, so the key idea is to use a function which capture how different the true value and the estimated value of the parameters are. Okay, so larger the value of the loss function, obviously the worse the estimated result is. Okay, so for example, okay, there are like some example of the loss functions. I mean, for example, like quadratic loss, okay, or like absolute loss, okay, or 0-1 loss, okay. Quadratic loss is like normally we get that and divide it by a number of samples. Absolute loss is also we get that the summation of the absolute loss and divided by a number of samples. And the 0-1 loss, we just get like the number of like samples that are different from in which like the prediction is different from the data. Okay, so that's like the indicator function. I is the indicator function. Okay, so practice, we generally do not have the value of the true parameter theta at hand. I mean, we normally do not have that because the theta we have is just a posterior distribution, not a real value. Okay, so we can estimate. We have estimation in the form of posterior distribution, as I said. So what we can do is to find out the value of theta hat that minimize the expected loss function. So this is like we will transform this into like to minimize expected loss function. Okay, find the value of theta hat to minimize the expected loss function. So by expected loss function, okay, we mean the loss function averaged over the whole posterior distribution. Okay. So for example, I mean, here, okay, in this code, okay, we have two loss functions, the absolute loss and the quadratic loss, okay? And we will see here we use like, sampling, okay? Like, grid approach, okay? We divide like the region into 200 points. And we then plot the curves accordingly, and we will include the value of theta hat that minimize each loss function. I think like this is fairly easy. Loss f underscore a represent like the absolute loss function. The loss fb, okay, represent like quadratic loss function. And the computation should be fairly simple, okay? I mean, in Python programming. And when you plot it, okay, it looks like this. So you can see that different loss function will have the different theta hat at the minimum place. Okay, you can see obviously for I think like loss a, I mean the absolute loss function. Okay, the theta hat that minimize the absolute loss function is at 0.32, and the theta hat that minimize the quadratic loss function is at 0.33. So they are slightly different. And interestingly, you will see that, okay, the first value is the median of the posterior, and the second value is the mean of the posterior. Okay, so if you consider this, minimal, the expected, expected loss function, okay, the value that minimizes the expected loss function, okay, for quadratic form, it's like a mean. For the absolute value case, it's the mode, okay. This is not a formal proof. You can verify this by, computing mean, okay, the theta post. Theta post is like the posterior distribution of the theta, and if you compute it, it will give you the NP dot mean will compute the mean and give you that mean, and the NP dot median will give you the median of the posterior theta posterior distribution, and you can verify what I have just said, like by using these two function calls, and obviously this is not a formal proof. Okay. Take-home message is different loss functions are related to different point estimates. Okay, one possible question I can ask you is, can you prove? Okay, when you want to minimize, for example, like this quadratic loss function, the result is is a mean of the posterior. Okay, can you prove that? Okay. And also, the value that minimize the absolute value absolute value loss function is like a median. Okay, can you prove this? Okay, I may give you questions like that in your homework. Okay, this is like a little bit more mathematics, but you can try to check out if you can do it. So, having said that, okay, we talk about like those two different loss functions as example. So I mean, should we explicitly choose a loss function? Okay, if we want to be formal and we want to compute a single point estimate, okay, then we must decide which loss function we want. Okay, so if we want the single point estimate, I mean we must decide loss function. Okay, the opposite is also true. Okay, so if we choose a given point estimate, okay, we implicitly deciding a loss function already. Okay, so these two things, I mean, you know, are correlated anyway. Okay, so the advantage of explicitly choosing a loss function is that we can tailor the function to the problem. Okay, so not just like using the predefined like a rule, okay, which may not be suitable for our case. Okay, so for example, in many problems, the cost of making decision is symmetric. What do you mean by symmetric? Okay, it's not the same to decide whether it is safe or not to administrate a vaccine to children, okay, under maybe age of 5, and being right, that being wrong. Okay, so if you consider this one to be right, and to consider this decision problem to be wrong, I mean, they are they are a problem of two sides, right? So if it's symmetric, that means like okay, the loss function, okay, should be able to be used. Okay, if this is loss function for one, the other loss function should be the opposite, because they are symmetric, right? But sometimes we will find such a problem is not symmetric. Okay, so because this is so important, making a bad decision could cost thousands of lives, produce a health crisis. Okay, I mean, for example, like the COVID-19 vaccination situation in Taiwan. I mean, now I think we are okay, but I wouldn't say we are very good in terms of vaccination, because I have quite a few relatives who don't do vaccination very well, and because they are, I couldn't convince them to do that. I mean, unfortunately, I mean, so in Taiwan there are still people, I mean, suspect like vaccination. I mean, so that's like an important decision, obviously. Okay, so that could have been avoided by administrating a cheap and a safe vaccination, obviously. So if the problem demands, the problem is demands a symmetric decision, then we can construct a symmetric loss function. Okay, in other words, like two sides will have a different loss function. Okay, so it's also important to notice, as the posterior is in the form of numerical samples, because remember we do this by using the grids. Okay, so we can compute complex loss functions that do not need to be restricted by mathematical convenience. Okay, or just for the simplicity. Okay, so because you can see we actually draw this by, you can see here, here. We generate like a 200 grid points in a range of 0 and 1, and then we do that. So it's actually very simple, okay, very simple. You can use a very complicated loss function. That's not the issue. Okay? So in practice, it's not true that every time people use a point estimate, they are truly think in terms of loss functions, okay? Because, I mean, normally we don't consider loss function. We consider like point estimate. We just consider like some point estimate are very common in scientific fields. For example, people usually choose maybe median just because it is more robust to outliers, or use mean just because it's simple and familiar concept. Okay, or they think that their observed data is truly the average of some process. Okay, that's it. Okay, so it's like, you know, when we consider point loss, I mean, we normally do not, a lot of time we do not consider the or associated loss function, okay, behind our decision, okay. But I just want to point out that, okay, when you have a point estimate, okay, you implicitly choose a loss function behind your decision, okay? So then, well, we are moving to the Gaussian model, okay? We previously talked about the concept of Bayesian inference by using a beta binomial model, okay? And the beta binomial model is, you know, used for explanation of Bayesian inference. It's just because this model is very simple, easy to understand, and you know, it happens to have conjugate prior that we can show, like not only like a grid approach, but also conjugate prior. Okay, but there's another simple model that we can consider. Okay, obviously is the Gaussian, or what we call normal model. Okay, and if you still remember, I mean, we actually talked about Gaussian model or normal model earlier. I mean, when we talk about conjugate prior, because I told you, obviously, beta prior is a conjugate prior for binomial likelihood. But for Gaussian likelihood, okay, you can also use Gaussian prior. Okay, so and the Gaussian, okay, I mean, you can also use Gaussian prior because Gaussian prior is also the conjugate prior. Okay, by the way. So Gaussian are very appealing, okay, from mathematical point of view because, okay, they are, because of its simplicity, okay. First, the conjugate prior of Gaussian is Gaussian itself, okay, so that's the first benefit of that. Second, many phenomena, okay, can be approximated using Gaussian, okay, especially when there are many factors that affect this phenomenon, okay. So, for example, like every time we measure the average of something using big enough sample size, then that average will be distributed as a Gaussian, okay. So there's like a mathematical proof of this called like central limit theorem, okay, CLT, which is very famous in you know, statistics, okay. You can check out the Wikipedia page of the central limit theorem, okay, to see like when this is true and when this is not true, okay. So, or when it's more or less true, obviously. So basically, like, let me give you some example, okay. For example, okay, the height of a person, okay. By the way, like, if you remember, in the previous chapter, we talked about the height of like a number of American women. Remember? Okay. So if you look at the distribution, that distribution is a nice bell shape, right? And we use that to describe like a Gaussian distribution, if you still remember. And another example we use is the height of the door, which was manufactured like at 7 feet tall. Remember? I mean, even, of course, that one, I mean, the distribution is much narrow. Okay, it's much narrower, much concentrate at you know, central region. But I mean, when you look at that example, like closely, it is also bear shape. It is also like a Gaussian distribution. Okay, so it's because the height, okay, is like determined by a lot of different factors. Okay, such as trait of the environmental factors. I mean, if you are eating well, like when you are a kid, okay, and many genetic factors, okay, how tall your parents are, okay, so we get a nice Gaussian distribution for the height of adult people. Actually, if you look at any observation, like which are affected by many factors, as long as you collect a large enough like a data set, normally it's like it looks like a Gaussian. Okay, so in summary, Gaussians are easy to work with, and they are more or less abundant in nature. Okay, so hence many of the statistical methods, okay, that we already know or have at least heard of are based on normality assumption. Okay, so it's important to learn how to build these models, and then it's also equally important to learn how to relax the normality assumptions. Okay, I don't think we can talk about how to relax normality assumptions this time, but next week we'll be able to talk about this. Okay, so something surprisingly easy. Okay, in Bayesian framework, I mean, to relax certain assumptions, I mean, in the modeling is very easy. Okay, with modern computational tool, okay, such as PyMC3. So let's consider one example that we will use the Gaussian model. Okay, this is called nuclear magnetic resonance. Okay, resonance. I mean, NMR. This is a technique that is used to study molecules and such as human or yeast. Okay, yeast is like I don't know another term to describe that. In Chinese, 酵母. I mean, 你喝健健美啊，或养乐多，Yakult. Do you know Yakult? Okay, that type of drink. Okay, there are like certain living stuff like in that drink, right? It tastes good, and if you drink a lot, I don't think it's good for your health. But if you drink reasonable amount every day, I think that's good for health. I mean, so that type of drink contains yeast. Okay, so NMR allows you to measure different kinds of observable quantities that are related to unobservable and interesting molecular properties. Okay, so one of these observables is known as chemical shift. Okay, so we can not only get the chemical shift for the nuclei of certain type of atoms. Okay, and all of this is in the domain of quantum chemistry. Okay, and the details are irrelevant for this class. Remember, for Bayesian data analysis, I mean, a lot of people familiar or like a master in the Bayesian data analysis are people in respective research domains, such as in medical domain or in social science domain, or take this author as an example, his field is actually in quantum chemistry, so that's why he came up with this example. Okay, I'm not saying this is important consideration, because you can sort of like disregard like the problem and just consider, okay, the data set that he collected. Okay, so this chemical shift, okay, we call that shift because we measured a signal shift from a reference value. So, and chemical because the shift is related somehow to the chemical environment on the nuclei that we are measuring. But as I said, don't worry about this if you don't understand this topic too well. I mean, I don't understand this topic. I mean, myself either. Okay, so you just treat it as like as a data set that we collected from somewhere. Okay, so the choice of this example is based on author's expertise. I mean, he's into like quantum chemistry. Okay, so for all we care at the moment, we could just have been measured the height of a group of people, the average time to travel back home, the weight of bags of oranges, or even a discrete value like a number of sexual partners of the tokay gecko. You know gecko, right? A type of, like kind of like lizard or something. Okay. So I mean, basically all these are, you can treat them kind of like a approximation of like a Gaussian. You can approximate them by the Gaussian distribution anyway. I mean, the last one is, you may argue, well, Gaussian distribution is continuous. How come there's a number of sexual partners of the gecko? I mean, obviously it's discrete, right? But if you can approximate number, the integer, okay, by a continuous variable, then you can even, model that discrete like a case by Gaussian distribution. Okay. So keep in mind that we do not need our data to be truly Gaussian. Okay. We just need we only demand that a Gaussian is reasonable approximation. Okay. So to our data. So for this example, we have 48 capital shift values that we can load into NumPy array and plot by this following code. So we first get this data from here. Okay. Oh, by the way, this book, okay, that I use for the text as a textbook, okay, its code and its like data set are freely available. I mean, online. Okay. So take this one as an example. This is like a data set like provided by the author. Obviously, this is not like available outside. Okay, so you can search this textbook and search like where you can download the program as well as the data set of this textbook. Okay, and use it for your own purpose. Okay, for your own learning. Okay. And then, okay, you can use Arvi's plot KDE to plot this data, okay, and it will look like this. Again, this is kernel function, and the lower part indicate like the value of this 48 samples, okay, and obviously you can see this area, the samples are more concentrated in this area, right? And there's like there are two samples that are not in this range, in that range. These two samples are not in that range, right? Okay, so but you can see the majority of the samples are in this range. Okay. So, so this shape is looks like it's Gaussian enough, right? It's Gaussian enough. I mean, it looks like a bell shape. Of course, we have some outliers. I mean, 2 outliers out there, but I mean, well, it's not too far away from Gaussian. So, so we can model this. Okay, let's forget about the 2 outliers for a moment. Okay, and we assume the Gaussian distribution is a proper description of the data. We do not know the mean standard deviation. Remember, the Gaussian distribution has 2 parameters. One is mean, one is standard deviation, right? So for mean, okay, we don't know what the mean is. Okay, we don't know what the standard deviation is. Okay, but we can still model them. Okay, the mean, we can model this mean comes that, I mean, can be drawn from a uniform distribution with this LH represent the lower and the upper range of this standard deviation, of this uniform distribution. Okay? And this sigma, the standard deviation, is also a value that we draw from this positive normal distribution. Okay, the positive normal distribution is just like because, well, it's a average at 0, and with standard deviation sigma sub sigma. Okay, eventually this LH and the sigma sub sigma will be given, okay, based on our experience. These two are considered prior. And once we have them, this is our likelihood. Okay? Remember, like, the idea, okay? If we don't know a parameter, we put a prior to it. Okay? So we don't know the mu, we don't know the sigma. So we put the prior to them. Okay? So one, it's a positive normal. I think the positive normal is fairly simple to understand. And why we use the positive normal to model the distribution of the of the standard deviation value? It's because standard deviation has to be positive, right? It has to be positive. You cannot have a negative standard deviation, right? Standard deviation is a square root of something, right? So it has to be positive. Okay, so in the Krusk style diagram, it looks like this. This is called like a half normal. Okay, this is called half normal. Okay? So we get the mu from this uniform distribution. We get the sigma from this half normal. And this is the data we sampled. This is distribution we sampled the data from, okay, which is normal distribution. And when we convert this into like a PyMC3 program, okay, it looks like this. Again, it's so simple, okay? And here we set the L to be 40, H to be 75, which is large enough to include all the values in the data set, okay? Which should be enough. But if you don't know, we can set L to be 0, H to be 100 if you want. Okay, you can even further relax it. Okay, so again, this prior choice is determined by your prior knowledge about this problem. So of course, like the author is in this research domain, so he think like using 4075, okay, that accounts for all the data value, all the values. I mean, in the data set should be enough. So you can see we said, okay, lower equal to 40, upper equal to 70. Okay, this is uniform, PM dot uniform. Okay, and we get this mu from here. Okay, and we use the sigma. Is drawn from this half normal. Okay, with standard deviation 10. Again, why do we use this 10 as here is based on the author's research background. Okay, just a large value. This is already pretty large value. Okay, for the data. Okay, if you don't know a good value, of course, you can even set this value to be even larger. Okay, I mean, to make it like a not restricted to a certain smaller range. Okay, so you set this here. Sorry. Okay, SD equal to 10, and then with the mu and the sigma. Okay, then you specify mu and the standard deviation sigma. Observable equal to data. The data is you received, you load it from a particular file here, right? Where? Here. Okay, and then, okay, you try to hit the inference button. Okay, again, you tried 1,000 samples. I mean, and you put the result to trace G, and then you use a plot trace to plot the result. Okay, and when you plot this trace G result, you will find that it will give you two sets of the figures. Okay, why? It is because, remember, we have two parameters. Okay, in this example, we have two parameters. One is mu, one is sigma. Okay, so actually, okay, for this particular example, the result is really I should say three-dimensional. Okay, with x and y being mu and the sigma, and the data point being the third, the value of y to be the third dimension. Okay, but for like plot trace function, it will just plot this two-dimensional result. I mean, actually, you can see that these two are marginal probability distribution for mu and the sigma. If you want to see the joint probability distribution, okay, you can use plot joint, okay, and feed in the trace G, and then it is going to give you the joint probability like this. Well, it looks like well, sorry, I don't know English term for that, but like some map will give you this, right? To show a mountain like this, 等高线图. Okay, because it's three-dimensional. I mean, the plot joint, okay, basically allows you to see the result from above. Okay, with different color will indicate like a different height. Okay, and the x-axis here indicate the value of mu. The y-axis indicate the value of sigma. Okay, something like that. It's three-dimensional, but well, that's the best it can do. Okay. So, well, and you can also output a summary of the trace, such as mean standard deviation and 94% HPD for mu and sigma. Okay, from the trace G. Okay. So, well, it's actually, well, because it's I have to go to a meeting like at 12 o'clock, so I think I have to stop here. So I will try to finish this example next time. Okay. In the following, we are going to try to use posterior predictive check to see if this result is plausible. Okay, is valid or not. But sorry, because I'm running out of time. So we will talk about this next time, okay? Yeah, so I'll see you next week. And remember, I will assign the homework 2 and put it on the E class, like before our next class, okay? See you next week. I want to remind you guys again that I believe the homework 2 has been posted to E class, okay? So if you have not downloaded it, I mean, please check it out. Okay. The due date is like next Friday, so you have about 10 days to work on that. I just hope that you guys will have a good spring break. So I set the deadline prior to the spring break. Okay, so that's it about the other stuff. So I'll come back to the material that we covered last time. Okay, remember we used we talked about a strange chemical shift stuff. Remember, and we try to model this by a normal or Gaussian distribution. Okay, which has two parameters. One is the average mu, okay, mean. The other one is the standard deviation, sigma, okay? And mean, we model it from a uniform distribution, and for sigma, we model it from a half normal, okay, because sigma is always positive, okay? So, and then we use the pi MC3 to generate the result. Because it has two parameters, so we have two of these. And the reality is that it's going to look like a three-dimensional, so we are able to see the joint distribution, something like this. Okay, I mean the top-down view, okay? So we talked about this last time, but yeah, this is the summary of the posterior for the mu and the sigma, okay? Of course, these represent the marginal probability distribution summary, because the whole thing is a joint probability anyway, okay? So, but is this model good enough? Okay. We learn how to critique the result at the end of last chapter, okay? If you still remember, we call that posterior predictive check, okay? And we only talked about the concept, okay? But we really didn't offer example at that time because, to really do posterior predictive checks, we need program, we need computer to help, okay? But now, okay, in this chapter, since we now know pi MC3, so we are able to do this posterior predictive check. If you still remember, okay, what we are doing is that we sample the parameter from the posterior, and then we use those sampled parameter, in our model, okay, and because we have a likelihood, remember? So from the likelihood, we are able to generate data, okay? It looks like a prediction, okay? It looks like a prediction. So the whole thing is called, that's why the whole thing is called the posterior predictive check, okay? Because we want to see if the data generated from the posterior along with the model, okay, how well the data match our original data, okay. So yeah, so we're using posterior to make predictions. So we are using these predictions to check the model. So So now, okay, with the help of the PyMC3, okay, we are able to do that, okay. So first thing first, okay, we need to generate the samples from the posterior, right? So here is the thing, okay. So, well, actually, PyMC3 is they already built a posterior predictive check, function, okay, for us. That's this one. Sample posterior predictive, and in this function, okay, remember the process of the posterior predictive check. You need two things, okay, to really generate the data. The first thing is the trace. This trace represents the posterior, right? The trace contains the posterior of the parameter, right? And then you can sample from this posterior. After that, you put this sampled parameters to the model, because model contains the likelihood, right? And then you have a likelihood, you are able to sample again from the likelihood. Okay, so here, okay, you put this trace G, which represent the posterior, and also you provide the model G. Okay, this one tells like this function, like what is the likelihood, okay, that it can use to generate the prediction, okay, that 100 just means like you want 100 like predictions, okay. So after you have that, okay, you store this result here, y pred, okay, g, okay. This y pred g is a dictionary, okay. Why is it a dictionary? Okay, because for a model, okay, we could have more than one observed variable. I mean, so far, like the examples that we have, okay, we have only one value. For example, like coin flips, okay, it's either like head or tail, or like this shift stuff, like the y that we are talking about, okay, is this thing, right? These values, okay. So yeah, I mean, for the existing the examples that we have talked about, okay, I mean the model, okay, is built for like just like single value, okay. Even though sometimes model may have one parameter or more than one parameter. For example, like in a coin flip, like we only have one parameter, which is the theta. Okay, for this gamma, normal distribution. Okay, we have two parameters, mu and the sigma. Okay, but the eventual data. Okay, for data. Okay, we always have like just one single value, but this is not always true. Okay, sometimes for some experiments, we may have like more than one data. For example, okay, say like if you want to collect like the location data. A location data comes with two dimensions, right? I mean, suppose we are collecting two-dimensional location, right? So it comes with two dimensions. And there are other vast examples, where the data may be multidimensional, okay? So that is why, okay, in this posterior predictive check, okay, the function, okay, generate this dictionary, okay, type of variable, which, I mean, is able to accommodate, okay, like, you know, if the problem you are dealing with, okay, happen to be multidimensional, okay. So, okay, then we can use the plot PPC function, okay, for visual posterior predictive check. So here, okay, is the code, okay, that we plot this next figure, okay. So if you still remember, okay, the dark line, okay, represent the observed y, the kernel function, function of the observed y. You can consider that as like a smooth, like a smooth histogram, okay, a smooth histogram of this thing. Remember, just this thing. Okay. But you may ask, what are those like wonky, you know, like a blue, like hairy lines behind? Okay, basically, okay. Remember, we are generating 100 samples. Okay, so each sample we try to draw you know, a kernel function, just like what we did for the real data set. Okay, and yeah, so because we generate like 100 samples, right? So each one will be represented by well, is it blue, right? Blue line, okay. You should be able to observe. I mean, so we have many blue lines, okay. And you first, of course, you check the consistency between the real data and the generated one, and see like if they match in certain aspect, okay. How do you think, by the way? Do you think it's good enough? Any comment? No comment? Okay. First thing first, if you really look at this, I mean, a little bit closely, you would have found that, okay, the center, okay, probably I shouldn't use center, I should use mode. The mode, okay, of the real data is here, right? Okay, the highest point is here. But if you look at the samples, the lines that I mean generated by the samples, it seems that the average or mode move a little bit to the right, right? It doesn't match so well, okay? It doesn't match so well, okay? So, is it good enough? Okay. Of course, okay, to really have a final saying whether or not this is represented, the result of the model is representative, okay, again, it requires certain background knowledge at this particular research domain, which is like quantum chemistry stuff. Okay, I don't know about that. Okay, but remember I told you. Okay, the author is an expert in that. I mean, research field. He has been working on that. I mean, for a long time. Okay, so basically, okay, yeah, I mean. So this KD is drawn by the obvious, okay? So, yeah, I mean, I already explained this, but okay. From the figure, we can see the mean of the simulated data is slightly displaced to the right. This is, I hope this is obvious. It's not, if it's not, I mean, you probably want to use the computer to generate it because, when we print it on the paper, it's not as clear as it is to the computer screen. But one thing is that, okay, you may wonder, like, why don't we, draw those 100 lines darker, okay, more thicker, okay? It is, I mean, it is because, like, it's, the author claimed this is a feature of RVs, okay? Some people will think this is a bug, okay? But the author thinks this is a feature, okay, because it reflects the property that of the data instead of almost over smoothing it. Basically, like, I mean, this data, the predictions, okay, of these 100 samples, obviously, I mean, are probabilistic, right? We generate this, I mean, using the sampling technique. So we sample the posterior, and then we sample from the likelihood. So obviously, I mean, because they have this probabilistic nature, so the author think it is reasonable to draw those lines like with like a lighter color, okay? But well, anyway, like if it's not, it doesn't look clear to you enough, well, you can certainly like just run this program on your computer and see the result by yourself. It's probably easier to observe. Okay, so come back to this explanation. Okay, so also the variance seems to be larger for the simulated data than the actual data. So let's take a again, this is probably a little bit more difficult to observe, okay? First, because if we want to observe like the displacement of the mean, okay, that's probably easier because, well, you just look at like the top of the line, okay? That's easier. But if you want to see like, how much deviate, okay, the predicted samples, okay, is from the mean, okay. That's a little bit difficult to observe, but just want you to be just want you to notice what model do we use. We are using Gaussian model, right? Normal Gaussian, right? So when you have a Gaussian model, when you have a normal model, it's a bell shape, right? It always is a bell shape, right? Okay, once you have sampled your sigma and your mu, okay, from the likelihood, okay, and when you draw your data, I mean, into a line, okay, it is going to be a bell shape, right? it is always going to be a bell shape, right? And the original data, okay, well, you have two outliers here. Remember, if you do not look at those outliers, obviously it's much concentrated. The data is much concentrated to the center, okay. But the generated, mu and sigma, okay, because of the outlier, because it has to take care of the outliers as well. So the sigma will be slightly larger in order to accommodate the outlier. Okay, this is the, you can see from the fact that, here, most of the lines are, much wider here, right? You cannot observe from the top, but you can observe from here. The data, the generated lines are, what should I say, like much wider. It's not as concentrated as the dark line here. Okay, because it is higher here because it has to accommodate these two outliers. Okay, that's why. Okay, it has like a there like the variance is are larger. Okay, for the simulated data than the actual one. Okay. So, but whether or not, okay, we can say the model is faulty and needs to be changed. Okay, remember we can, even though we can observe these two differences, but those differences are kind of minor, right? Well, it's the mean moved to the right a little bit, and the variance is slightly larger, but both are not that far away from the actual data. Okay, so as I said, the interpretation of the model and its evaluation is context dependent. What do I mean by context dependent? It depends on the domain expert. Okay, so based on the author's experience, okay, to this research area, okay, he said he thinks like this model is reasonable enough representation of the data and useful for most of the analysis. Okay, so so in Bayesian data analysis, okay, you have to work your model with the domain scientist. Okay, you cannot, or you have to become the domain scientist of that field. Okay, otherwise, like a lot of times when you analyze, when you do certain analysis, like you need like the result is context dependent. When it comes to a situation like that, you need the domain scientist's help to see if the result is presentable, if the result is reasonable. Okay, but of course, okay, how about those outliers? Okay, the reason of the displacement of the mean as well as like a slightly larger of the variance, okay, remember, are really caused by those two outliers, right? So what can we do with outliers? Okay, can we deal with those outliers beforehand? Okay, so one objection, okay, I mean, you may have, okay, with this model, with the normal, we assume the model is a normal distribution, okay, it's a Gaussian distribution model, okay, but we have these two data points, okay, and they obviously do not look like Gaussian at all, right? So these two outliers make this normal assumption, not as natural, okay, as we anticipated, okay. So what do we do? Okay. So we can one thing we can do, okay, one possible solution, okay, we can remove those outliers. Okay, in statistics, okay, there are rules that allow us to remove outliers. Okay, so or we can even fix the outliers. I mean, if we know exactly what causes those value to be like that. For example, if we can fix the data point. Okay, if we realize they are just a result of bad coding. Okay, I mean, if it comes from a bad coding, I mean, once you fix your program, of course you are able to correct those errors. Okay, or you remove them, as I said. But so this type of research, okay, how do we deal with this like noisy data? Okay, we want to, I mean, when there are too much noise in the data, we want to, make the data set, look more consistent. Okay, this type of research is actually called data cleansing. Okay, cleansing the data, cleaning the data. Okay, this is actually one of the important research topics. Okay, because I have a paper on that in the first year conference. Okay, data cleansing is important stuff. I mean, at that time we were doing like RFID research. Okay, I mean, I'm not sure. I mean, because we are talking about like the passive RFID tag. Okay, the one that we use for for example, like your student ID or your credit card, or the one that is on like Yo-Yo car. Okay, basically like those are passive RFID tags. When we do some experiments, I mean, there are, several outliers. So how do we model those outliers to get rid of them? Okay, so those are was an interesting question, because back like about 10 years ago, a little bit more than 10 years ago, RFID research was very hot. Okay, so anyway, okay. So here, okay, if you only want some simple rule, okay, to deal with outliers, what do we do? Okay, these are the two rules that we normally use to get rid of outlier. Okay, the first, any data point below 1.5 times of the interquartile range from the lower quartile, or 1.5 times the interquartile range above the upper quartile, is an outlier. First, I mean, do you know quartile? No? Okay. It's called, in Chinese, it's called 四分位数. Okay, you know the mode, right? Everybody know the mode, right? 中位数. Okay, so, So say like if this is if this is the distribution of your data, okay, the mode, okay, the 中位数, okay, is normally at the middle, right? Normally at the middle, okay. Or when you can sort your data, okay, according to certain ranks, okay, and the one in the middle will be the mode, right? We know that, right? And then this is like a 1/4. This is 3/4. So this is the first, the what we call by the lower quartile. This is lower quartile. This is what we call upper quartile. Okay. Okay. So the only thing that left unanswered is what is the interquartile range, right? The interquartile range is the size, okay, between your lower quartile and upper quartile. So this is your, this range is called the interquartile. Okay? So if it's like, 1.5 times of the interquartile range, lower than the lower quartile, or 1.5 times interquartile range, higher than the upper quartile, we consider that outlier. Okay? So this is one way to get rid of the outlier. Okay? The second way to get rid of outlier, okay, these two are not, okay, applied simultaneously. You could, but normally we just pick one. Okay? We just pick one. Okay? So any data point below or above 2 times of the standard deviation of the data, okay, we claim them outlier. Okay, the second one is perhaps more commonly used. Okay, to be honest with you. Okay, but both are valid. Both are valid. Okay. So obviously, if you apply one of these two rules, you may be able to get rid of the, it looks like you are able to get rid of these two outliers, because like it looks to us like the mu should be somewhere here, and the standard deviation should not be too far away from it. So let's consider the second rule. Okay, so twice of the size of the standard deviation from the mu. Okay, it looks like this. I'm pretty sure this will be removed for sure. For this one, it's probably at the margin. Okay, very close to be removed. Okay, but so this is like how statistics consider what outliers is. Okay, but even though the traditional statistics consider like the outlier removal from the data directly. For for Bayesian's approach, okay, Bayesians prefer to encode assumptions directly into the model, okay? So this is, the outlier removal rules are not favored by the Bayesian data analysis, actually. The Bayesians prefer, okay, to encode these assumptions in the model, okay? I mean, what do we mean by that? We can use different priors and likelihood, okay, to take care the outliers, okay? Instead of using those heuristic rules to get rid of them. We can take care outliers by using different prior or likelihood. So the following is the solution, like that we could use, okay, when we see like outliers, I mean more outliers in the data set, okay. Basically, okay, you know, we can replace the Gaussian model by what we call student t distribution. Okay, so what is student t distribution? Okay, a student t distribution has 3 parameters. Okay, remember in Gaussian distribution we have 2 parameters. We have mu, we have sigma, right? And everybody knows what mu and sigma are. So for student t distribution, we have 3 parameters. Okay, the first one is the mean, which basically is the mu. Okay, just like the Gaussian distribution. Okay, and the scale. Okay, kind of can be you know, can be or like is comparable to standard deviation, but be very careful with the wording here, okay? They are not exactly the same, okay? But they are in some way similar, in some way similar. And the third one is, you know, nu, okay? Greek letter mu, okay? Nu, nu, okay? If you are not into Greek letters, if you want to call it V, I mean, I'm okay with that, okay? But that's called degree of freedom, okay? Degree of freedom, okay? So this model is kind of interesting, okay? So this nu or V, okay, is called normality parameter. Why do we call it normality parameter? Because it is, you know, it controls how similar the t distribution is to a normal distribution. Okay? So, you know, keep in mind this nu or v, okay, is in the interval of 0 to infinite. Okay, 0 to infinite. So when this nu v, okay, is 1, okay, so let's just like fix the naming of this one, okay. Let's call it v, okay, because it's probably easier for you to remember, okay. But keep in mind, okay, in Greek letter, okay, this thing is called nu, okay. So later if you see like we refer this one as a nu in the slide, okay, you need to remember which parameter we are referring to, okay. So for a value of v equal to 1, we get distribution with heavy tails. Obviously, normal distribution is not heavy tail, right? Okay, so this is not normal distribution, okay, but it is known as Cauchy or Lorentz distribution. Okay, you don't need to remember those names because, in some sense, like this, we can just use t student distribution. It will cover this distributions anyway. Okay, so by heavy tail, we mean it is more probable to find values away from the mean compared to a Gaussian. Okay, so because of this nature, okay, because of this nature, students' t-distribution is able to handle outliers much better than Gaussian distribution. Okay, so so it is not as concentrated to the mean as in the light tail distribution, like Gaussian. I mean, when we say light tail, it means like it's more concentrated to the center. Okay, so as an example, 95% of the value, okay, from the Gaussian distribution. I mean, in this case, it's like when the v is 1, right, in the student t distribution, okay, are found between negative 12.7 and positive 12.7. Here we are talking about like a mean zero, just like standard deviation. Okay, the standard deviation, we know like for the standard deviation, or sorry, what do I say? For normal distribution, standard normal distribution, okay, or standard Gaussian distribution, okay, with mean 0 and the standard deviation 1, okay, we know like for Gaussian distribution, normal standard Gaussian distribution, okay, the 95% of the values, okay, will occur between negative 96 to positive 1.96. You can see, you know, these two, I mean, when you compare these two, you can see how heavy-tailed the Gaussian distribution is, okay? So on the other side, okay, when v approaches infinity, okay, we get a Gaussian distribution. So basically, this v value control how similar the student t distribution is to the Gaussian distribution. So you can say student t distribution is very versatile, okay? So there are some factors we need to be very careful, okay, when we set up these values, okay. So for example, it has no defined mean when v is small or equal to 1. What do we mean? When v is small or equal to 1, it has no defined mean because it's so heavy-tailed. So, you know, when you sampled from this distribution, okay, it's very likely you get like a bigger and a bigger value. Oh, I mean, or like a or smaller value away from the mean. Okay, so as a result, okay, you cannot get you know a stable mean. Okay, I mean, if your student t distribution has a v value small or equal to 1. Okay, so this is something you need to be very careful. Okay, so so in a similar fashion, the variance of this distribution is only defined for value of v greater than 2. So if the v is small or equal to 2, okay, there's the standard deviation, okay, you know, cannot be defined, okay, variance, okay, no defined variance, so no defined standard deviation. So these are some special constraints for student t distribution. Okay, but that's okay. I mean, remember, I mean, in Bayesian data analysis, we just, if you don't know something, we put a prior, and then we just let the data to decide where that value is more suitable. So we are not the one who decide the value of v or the value of like scale. Okay, scale. Okay, so scale of the student t distribution is not the same as standard deviation. Okay, I just want to keep, I mean, remind you again. Okay, even though I say in some degree they are similar, but they are different. Okay, scale and standard deviation become closer and closer, okay, when v approaches infinity, okay? So that is why I say they, in some aspect, they are similar, okay? But when v is finite, this statement is not correct, okay? Okay, so, well, it's about time. Let's take 10 minutes break. When we come back, I will show you some t-distribution figures, and so that you can get a better understanding about that. So this is just the code that draw like student t-distribution. Okay, I don't think I need to go through all this code, but you can see that, okay, here, okay, it used like the 1, 2, and the 30. Okay, in this for loop, it used 1, 2, and 30 to represent the value of the v. Okay, and to draw 3, student t-distribution along with the normal distribution. So you can see the dotted line is the normal distribution where v is infinite, okay? And when v is 1, okay, it's represented by the blue line. V is 2 represented by the orange line, and v is 30 is represented by the green line. You can see that when v is 30, it's already very, very, very close to the normal distribution, right? Almost like overlapped, but still a slight different. But you can see 30 is already pretty close to normal distribution. But when v has a smaller value, obviously you can see that the distribution is more what we say like heavy-tailed, right? I mean, it disperses to the both sides, right? Okay, so that's like the nature of the student's t-distribution. Just want you to get an idea of this. Okay? So with that in mind, okay, we could use the student t-distribution in our model. So, okay, so originally we use a normal distribution here, but now we use the student t-distribution. And remember, I mean, if you use student t-distribution, we have mu, sigma, and v, okay? Well, sigma represent the scale, okay? Even though I say scale is different from standard deviation, but we actually use the same notation as standard deviation. But keep in mind, it is really not the standard deviation, okay? But it has some similarities, I mean, between these two, okay? And that v, okay, actually should be pronounced as nu, okay? But I mean, because we have that, well, we have that parameter. So obviously we have to also, design a prior for that parameter, right? So what do we do? Okay. Here we set this v, okay, or nu, okay, to be to draw from the exponential distribution. Okay, the exponential distribution with mean lambda. Okay, and so what do we set? What do we set for this lambda? Okay, so we know, like for example, when v is 30, it's already very, very close to the normal distribution, right? So, and we think like we want it to be, kind of similar to our original model. I mean, normal distribution model. So we set this mean to be 30. But keep in mind, this is a weakly informed prior. Okay, so we more or less think v should be around 30. Okay, in other words, the model should be a little bit close to the normal distribution, but we can move to smaller and larger values. Okay, easily. Okay, because the exponential distribution really like is a very like weak like it's not concentrated on 30 that much. Okay, so this is a result. Okay, and we draw the diagram to represent this model. Okay, so this is like we use student t distribution, and on top of this, I mean, we have 3 parameters where mu comes from the uniform distribution, and the sigma comes from the half normal, and the v or nu, whatever you call it, comes from the exponential distribution. So and the uniform distribution, the L and the H remains the same. Okay, half normal, yeah, again we use the same setting. Okay, the only thing we modify is we change this this one from the normal distribution to t distribution, and we have extra additional like prior for the additional parameter v. Okay, so as a result, okay, this is the Pi MC3 code. Okay, so you can see we have mu, okay, which is uniformly distributed in the range of 40 to 70. Okay, and sigma, okay, is from the half normal with standard deviation 10. Okay, which these two are the same from, I mean, our last example, and the sigma. Sorry, the v, okay, the v, okay, is an exponential distribution with average 30. Keep in mind, okay, the exponential distribution, okay, the lambda is represented as like 1 over this average. Okay, so then we have like the student t. Okay, so well, the result is generated by, as I mean, indicates a y, and we have mu, we have sd, we have nu, because v is really like, because it's a Greek letter, it's really pronounced as nu. Okay, so observed equal to data, and then we call this model as where is it? This model T, okay, which is different from model G because the model G use Gaussian. Here, model T use student T distribution. Okay, and then okay, we use a sample method to generate 1,000 samples from for each chain. Okay, and how many traces depends on how many core you have in your GPU, again. And we store that trace in the trace T, okay, and then we plot this trace. And the result is going to be like this. So you can see the mu and the sigma are really not too far away from the previous example. Yeah, because, well, they are, you know, they represent the mean and the standard deviation, kind of standard deviation, right? As I said earlier. So if you compare it with like the previous one, okay, that we used the normal distribution, I mean, it's not too far away. But one thing interesting is for nu or for v, okay, you can see obviously, okay, originally we said the average to be 30, but now you can clearly see that the average is much smaller, right? It's much smaller. Okay? This is why. This is because, remember, we have those two outliers. Those two outliers, you know, make the resulting model heavy-tailed. Okay? And in student T distribution, when it is heavy-tailed, that means your V value is going to be smaller. Okay? So let's take a look at this summary of trace. Okay, so so you can see mu is now 53, sigma is 2.2, and this v or nu, okay, whatever we call it, is 4.5. The mean is 4.5. So that means like really like this model, okay, is what should I say? It's not as close as no distribution as we may originally think, okay? Because when the mu is larger, okay, maybe close to like 30, it looks more like a standard deviation. Sorry, more like a normal distribution. But now the V is only the average. The mean is only 4.5. Okay, and if you compare it with the result of the Gaussian model, you will see here. You see the mu. Okay, originally if you use Gaussian distribution, you see the mu was 53.45, and now I mean if you use a student T distribution, we have 53, right? So it's about like a 0.5 lower, which is good. Why? Because it means that, remember I told you, okay, the mean actually, okay, in this case is slightly larger, right? And now we are able to move it like a 0.5 back to the real data. That means it matches with the data better, okay? But you see, for standard deviation, originally it's 3.54. Okay, now it's 2.2. So we are able to reduce this variance, okay, a lot. Okay, because 3.52, 2.2, the reduction is like you know, more than 50%, right? Okay, well, depends on how you say it, but well, at least 30% reduction, right? So this reduction on like variance is much better. And remember, the two issues we talked about for the Gaussian model. Okay, first, the mean is slightly, you know, displaced to the right. Okay, it's fixed, and also the line. Okay, as I said, like it's not as like it is. the variance is larger, okay, compared with the real data, it also get fixed. Okay, so this is how the Bayesian data analysis deal with outlier. We don't use outlier removal rules. Okay, we could do that. Okay, but we do not prefer to use these rules to manipulate the data. I mean, instead we just build the constraint in the model. Okay, because we know that student t-distribution is able to handle outliers much better than the Gaussian distribution. Okay, so this is how we do it. Okay, so the estimation of mu, okay, between both models similar with a difference of like 0.5, which is better because it actually move the mean closer to the real data, the mean of the real data. Okay, the estimation of the sigma changes from 3.5 to 2.1. So it's a consequence of the student t-distribution giving less weight by values away from the mean. So again, this is good because it matches the real data much better. And we can see V is only 4.5. So we have a not very Gaussian-like distribution. So it's a heavy-tailed, okay? We can do this posterior predictive check again, okay? Well, the code is similar, okay? And then, okay, I will not go into a detail of this, but just call the sample posterior predictive, okay, and pass the trace as well as the model to it, and also like set like how many samples you want, and then you're able to plot it in a figure, and you can see that this result is much more consistent with the real data. Okay, and you could compare this slide with like with this slide. Okay, I mean, I'm sorry because these two slides are far away from each other, but if you put them against each other side by side, you will see that student t-distribution model capture the real data much better than the Gaussian one. I'm not saying Gaussian one is very terrible, okay? Because as I already explained, like the domain scientist, the domain expert, consider this is good enough, okay? But I'm saying like the student's t-distribution model is better, okay, than the Gaussian model, okay? Okay? So, student t-distribution allowed us to have a more robust estimation because outliers have the effect of decreasing V, okay, instead of pulling the mean toward the outlier, okay, and increasing standard deviation. Okay, there was the effect, I mean, that we can observe, I mean, in the Gaussian model, but not, I mean, that outlier only affect the value of V, okay, in student t-distribution, which is good, okay, which is good, okay. So the mean and the scale are estimated by weighting more data points from the bulk of the data than those apart from it. So we actually get like the mean and well, the scale actually, as I say, is closer to variance, closer to the standard deviation, more from the data here. Okay, the outliers, I mean, well, they affect, I mean, only the V or nu, okay, in the student t-distribution. Okay, so once again, it's important to remember the scale is not the standard deviation. Okay, but the scale is related to the spread of the data. So when you consider scale is related to the spread of data, it will be similar. It is similar to standard deviation in certain manner, right? So the lower its value, the more concentrated the distribution. So you can see that, okay, based on this result, student t distribution, the scale is very, very similar to standard deviation, okay, in terms of their impact, okay, to the distribution. So for the value of v greater or equal to 2, the value of the scale tends to be pretty close, okay, to the value estimated after removing the outlier, okay. So even if you remove the outlier, okay, the scale tends to be very close. So you can see that, okay, student t distribution is able to handle the outlier, much more robust than the previous model, okay. So rule of thumb, for values of v not too small and taking into account it is not theoretically fully correct, okay. Remember, the model is always an approximation, so it is not, okay, we cannot consider model is 100% correct anyway. We can consider the scale of a student t distribution as a reasonable practical proxy, okay, for standard deviation of the data after removing outliers, okay. So another type of question that we commonly considered, okay, is like a group comparison. Okay, what is group comparison? Okay, so we may be interested, for example, in how well patients respond to a certain drug. Okay, so in that case, you have like maybe two groups. Okay, one group, do not take. The patient in that one group do not take the drug. The patient in the second group takes that certain drug, and then we compare the response of these two group of patients. Okay, after a period of time. Okay, so this is group comparison, or okay, the reduction of car accidents by the introduction of a new traffic regulation. Okay, for example, like we recently, because we know Taiwan is gets a bad name for it's a hell for passengers, right? When we passenger walk on street, sometimes the cars just they don't give ways to passenger, right? So recently, government passed regulations, if the car does not give way to a passenger, the driver will be fined, right? Okay, fined heavily, right? I probably should add that. Okay, it'll be fined. The driver will be fined heavily. So this is obviously a new traffic regulation, right? So with this traffic regulation, okay, we want to see the reduction of the car accidents. Okay, if there are fewer number of pedestrians, be hit by the vehicles, okay, on the street. Okay, we want to observe, okay, if this is the case. Okay, so again, we have two groups. The first group is before this regulation is in place. Okay, what is the situation? And after we have this regulation, what is the new situation? So we have these two groups, and we compare to see if this new traffic regulation really has certain I mean, it really works or not, okay? So, or, okay, student performance under different teaching approaches. Okay, I'm here to teach you guys like in person. In some courses, the professor may prefer to teach like online, or some professors even do it like I don't know English term for that, 翻转教室, okay? So I don't know the English term for that. Basically, they just let you watch the video, right? And then they just let you do some practice, in class, right? So the professor may be in the classroom or not, okay? But anyway, that's a different like teaching paradigm, right? But anyway, okay. So there are obviously different teaching paradigms, okay? Of course, for me, I prefer teaching in person, okay? Whether or not student comes to a class or not, that's different issue, okay? I don't care, okay? I prefer to interact with the students directly. But okay, students may perform differently under different teaching paradigm, right? Okay, so for different teaching paradigm, we can observe student performance and see like which teaching paradigm work better, okay, for students. Okay, again, this type of thing, will be considered as a group comparison. When I say group comparison, I'm not restricting to comparing just two groups. It could be multiple groups, like for example, teaching paradigm. Okay, the example I just used, like because obviously you could have more than two different teaching paradigms. Okay, so sometimes this type of question is framed under the hypothesis testing scenario, with the goal of declaring a result statistically significant. Okay, so in the traditional statistics approach, okay, we use normally we use the NHST. Okay, basically we just have a hypothesis, and we just use we just try to see if we can refute, we can dismiss that hypothesis using like the collected data, obviously. So relying only on statistical significance can be problematic for many reasons. First, statistical significance is not equivalent to practical significance. Okay. Second, really small effect can be declared significant, okay, if you collect enough data. But this is not necessarily the case, okay? The third one, okay, idea of hypothesis testing, okay, is connected to the concept p-value. But I'm not sure if I think I mentioned about that, earlier, okay? The p-value that was proposed like in the traditional statistics, the frequentist, basically, has some built-in assumptions, okay? For example, one of them is like tied with like the intention of data collection, which is completely, a lot of times are completely unavailable, okay, when you do data analysis. Because a lot of times you get the data from somebody else who collect data for you. But you have no idea how this data was collected, okay? So, because under different intention of the data collection, the p-value can be very different, okay? Did I give you guys an example of that earlier? So for example, like flipping coins, okay, flipping coins. You say, okay, I got the data, okay, this coin flipping like is like we have like maybe like 5 head and 10 tails. Okay, 5 head, 10 tails. So you say, oh, so we collect 15 coin flips with 5 head and 10 tails. Okay, if you try to consider all the possibility for 15 flips, that is what? Okay, think about that. That's the whole possibility space, right? Of 15 flips, okay? But this is one intention. It's like, okay, I collect 15 flips, okay? I collect 15 flips, and this is the result. We have 5 heads, 10 tail. This is, okay, the original intention is to collect 15 flips. Another intention is, okay, I collect the data until I get 10 tails. And then the result is where we got 5 heads and the 10 tails. These two intentions will impact the computation of p-values. Okay? Depending on what the intention you have. You have, like, when you collect the data, you have to compute the p-value differently. And obviously, different p-value will impact the hypothesis testing. But when you get this, okay, I got 5 head, 10 tail from some people who do the experiment. Do you know what is the collection intention? When you get the data from somebody else, they may tell you, they may not tell you, right? Because you know the high school math, right? These two cases that I was mentioning, okay, the first one, throw 15 times of the coins, and the result is 5 tail, 10 head. 5 head, 10 tail, I'm sorry. 5 head, 10 tail. This is the first case. The probability, just use probability as example, okay? So what is the probability? So you can calculate that, right? Another case is, I want you to throw until you get 10 tail. And in this case, you got 5 head. I mean, in the process of getting 10 tails. So the probability of these two things are different, right? I mean, well, it's not just determined only by the resulting data set, obviously, right? So that's what I meant by, okay, those intentions, okay, they will impact this p-value computation, and which again will have impact, to your hypothesis testing. So in some cases, okay, you can refute a hypothesis. Some cases you cannot. But those factors are not determined by you, okay, and sometimes you don't have those consideration, those factors at hand when you do the data analysis. So how do you do it? So that will create a problem when you use NHST to deal with group comparison. Okay. So, but the people are used to doing group comparison. By, for example, NHST, because that's what they learn in most introductory statistical courses. Any statistical courses teach this type of stuff, as an introduction to statistics. If you take if you are going to take graduate school entrance exam, and it happens that one of the subjects is statistics. I'm pretty sure, okay, it will cover HST, okay, because this is one of the fundamental concepts in the introduction to statistics courses. Okay, so a lot of people just have studied this thing, and they consider this as like a standard practice, but in Bayesian data analysis, we consider this approach not appropriate. Okay, so instead of doing hypothesis testing, okay, so we are going to take different approach. Okay, so we are going to focus on estimating the effect size. Okay, what is effect size? We need to quantify the difference between two groups. Okay, here, of course, I say difference between two groups. I mean, we can, if you have more than two groups, I remember I just mentioned, I mean, it could be more than two, right? So if you have more than two groups, we can compare, we can do this computation for like every two groups. Okay, I'm not saying this doesn't work for more than two groups. So so just want you to be aware. But every time we just consider two groups. So one advantage of thinking in terms of effect size is that we no longer consider just yes/no question. Okay, we are able to consider like how well, okay, does a particular factor work, okay, or how large or how small is the effect, because we are able to compare this, consider effect size. So this is much, what should I say, like a much more complete estimation. Okay, it's not just like just give you yes, no, because like NHST, it will just tell you yes or no. Okay, so effect size is just a way to quantify the size of differences between two groups. Okay, so there are, of course, like we could have like a control group and a treatment group. Okay, when comparing groups, people talk about control group and treatment group. Okay, for example, remember the drug testing example I just mentioned. Okay, so normally we have a control group, we have the treatment group. The control group basically like are patients, contains patients who take a placebo. Okay, what is placebo? Placebo is like something similar to drug, but it's just, for example, just vitamin or something. Okay, it doesn't have any effect, but they will feed this placebo to those patients in the control group. And for the treatment group, okay, the patients in treatment group, they will take the real drug. Okay, the reason for the patients in control group to take the placebo is because like if you do not give them anything, the patients in control group may consider them to be abandoned, and the psychological impact for such a situation could be much bigger than you may imagine. Okay, for human, actually, like the mood. I mean, our mood impact our body. How our body works. Okay, I mean, when you are in good mood, okay, a lot of time your body works much better. Okay, but if you are in a bad mood, for example, you feel like you are abandoned, then your body will come up with something wrong. Okay, so this is like the reason to provide placebo to like patients in the control group is just to make sure, okay, such feeling is not it's not there, okay, for patients in the control group. I mean, hopefully it's not going to impact their their body, okay, because we want to see like how the body react to the drug. So with or without, okay, we don't want the psychological impact, okay, to play as a factor in this experiment, okay? So a lot of time when we do this experiment, we don't like the person actually like administer the testing. He doesn't even know who take the placebo, who take the real drug. Okay, it is it won't be revealed until the data is collected, and the result is like the analysis result is finalized, and then they will do like they'll review like this type of thing. This is called like a 解盲. Okay, 解盲in Chinese is called 解盲. I don't know the English term for that. Okay, but anyway, because like for past few years, because like we are hit by the COVID-19 pandemic, right? So a lot of countries are trying to develop like drugs for COVID-19. So this type of terms are more commonly seen in a newspaper. Okay, I mean, well, probably it's a good thing. Okay, for you guys to understand what that means. Okay, so one interesting alternative question will be to ask how good a new drug is compared with the already approved most popular drug to treat that illness. Okay, for example, like since I was talking about COVID-19, so let's just use COVID-19 as an example, because the new drug may be like the 高端, right? 高端. Again, I don't know the English term for that. Okay, it's a new drug developed by Taiwan. Okay, by Taiwanese people, and we know like there are like other drugs such as like what's the name? The one from the AZ, right? I don't know the full name for that. AZ which comes from like British, right? And US also has their drug, right? So those drugs are already approved, okay, and they are popular, okay. And we want to see, our 高端, okay, how good our 高端compared with those like popular drugs, okay, to treat maybe COVID-19. This is a lot of like this a valid question for like medical field. Okay, so in such a case, the control group cannot be a placebo. Okay, it should be the other drug. Okay, so it is not necessary that you have to have control group. It depends on your problem. Okay, some problem may have control group in the sense that in that case, like the control group basically try to do nothing. Okay, and the other group, like a treatment group, will you will put in like the factor that you want to evaluate to the treatment group. Okay, but in some other type of situation, there's no control group. Basically, like every group will have a different treatment. Okay, so as an example, okay, imagine you work for a dairy product company that wants to sell overly sugared yogurt to kids. Okay, and they will just tell your kids and the mom, tell your dad and mom that this particular yogurt boosts the immune system. Okay, immune system, right? So it's like the system that defend like disease, right? So help the kids grow stronger. Okay, so one way to cheat or falsely back up your claim with data is by using milk or even water as a control group instead of another cheaper, less sugary, less marketed yogurt. So the control group selection is important. Okay, if you compare with a group that is not what should I say, reasonable, then this group comparison result is not trustworthy. Okay. So when someone says something is harder, better, faster, stronger, remember to ask what the baseline used for the comparison. Okay. So I mean, yeah, I mean this is always the case. You know, for you, because in every lab, okay, because you guys, I believe many of you are associated with a certain lab, right? So no matter which lab you are associated with, you need to you need to work on certain research, and in the research, it is important to, you know, come up with a method, okay, which is better, cheaper, you know, stronger, more robust, right? But it is always about what baseline you pick, okay? I mean, if you don't pick a reasonable baseline, your claim is just not trustworthy. It's just false, okay? So there are 3 tools, okay, we can use, okay, for group comparisons, okay? So the first one, you know, this, remember we are talking about the effect size. So effect size is something we can calculate, right? We can calculate. This is kind of like a number, kind of, but not necessarily a number, as I will explain later. But anyway, okay. So how do we, you know, what are the matrix that we can use for effect size? Okay, there are 3 ways. Okay, so so we must decide which feature, okay, we are going to use for the comparison. Okay, so you know, very common feature is the mean of each group. Okay, so because we are Bayesian, okay, so we'll work to obtain posterior distribution of the differences of means between groups, not just a point estimate of the differences. So to be exact, we have you know, 3 tools. The first one, posterior plot with a reference value. Okay, we talked about this earlier already, right? We actually talked about 2 things. Okay, so for example, we could have a reference value. We could have a rope. Remember, we could have a rope. Okay, it's a region of like a practical equivalence. Remember? Okay, so I mean, so no matter you are talking about like a reference value or rope, basically is similar. I mean which are already covered. Okay, the second one is coherence D. Okay, what is coherence D? I will explain shortly. The third one is probability of superiority. Okay, these 2 are actually correlated in many cases. Okay, yeah. So let's continue. Well, so the first thing we already explained previous, so I will skip. Okay, the second thing, coherence D. Let's take 10 minutes break. When we come back, we will continue from here. Okay. Okay. Okay, so what is coherence D? Okay, coherence D is like this. The definition like this. Okay, for 2 given groups. Okay, assuming their mu and the sigma are mu1, mu2, and the sigma 1, sigma 2. Okay, respectively. Okay. Then their coherence D. The D actually stands for distance. Okay, D actually stands for distance. Okay, so obviously, okay, when you want, the difference of the mean is important, right? I mean, we want to measure like differences between two groups. However, okay, how significant is this difference of means? Okay, is also determined by their standard deviation. Okay, because, for example, like if you have like difference of 1, then if the standard deviation is in the at the scale of 0.1, then you should consider this difference is large. But if for the same difference of mean, okay, if the standard deviation is at a range of 100 or 10, okay, even 10, then that difference, okay, of mean will be less significant, okay. So that's why, okay, this Cohen's d is defined by in this format, okay. So we compute this pooled standard deviation and use that as like a denominator in the Cohen's d to represent like to normalize the difference of the mean, okay, basically. So Cohen's d is a way to measure effect size, okay, where difference of the mean are standardized by considering the poor standard deviation of the both group. So I already explained, okay. So yeah, so including the intrinsic variations of group is a way to put the differences in context, okay. So rescaling, okay, the differences help us make sense of the importance of difference between groups, okay, even when we are not very familiar with the scale used, I mean, for the measurement. So this is like how Cohen's d works, okay. In some sense, Cohen's d, okay, can also be interpreted as a z-score, okay. Do you guys know what z-score is? Z-score is like okay, you see how the difference of two values, but you measure it by by the number of like standard deviation. Okay, so for example, in one distribution, okay, you get like two values. How far away, I mean, do you consider these two values? Is you just consider the distance of these two values divided by the standard deviation of the distribution. So if the difference is like only like maybe 0.1 standard deviation, that's not much. But if the difference is maybe like 1 or even 2 standard deviation, that's considered a lot. Okay, so in some sense, Cohen's d, okay, is similar, right? Because you are dividing the difference of mean by like kind of like the scale of the standard deviation. So it's also similar to the, I mean, conceptually similar to the z-score. Okay, so so when the differences of mean are standardized, okay, just like Cohen's d, okay, we may still need to calibrate ourselves based on the context of a given problem to be able to say if a given value is big, small, medium, okay. So this calibration can be acquired with enough practice, okay. For example, okay, if I used to perform several analyses for more or less the same type of problems, okay, we can get used to a Cohen's d, for example, 1, okay. So when we get a Cohen's d of 2, then we know we have something important. So basically, okay, if you do this similar problem, if the previous coherence D is a small value, and this coherence, now you get a larger coherence value, then you know this value is more significant than the previous one. So it's more like a result of the comparison. Okay, if you do not have this practice yet, so you can ask a domain expert, okay, for their variable input. Again, because every time you see something, it's like based on the, for example, context of the problem, then you probably it will be a good idea, okay, to consult a domain expert. Okay, so for example, like a very nice web page to explore like a difference value of coherence D. You can check out this web page, okay, to get a more understanding of the coherence D. But if you don't have access to a domain expert, then you probably have to do more experiments, and through the comparison, you can get a sense of like which coherence D value. I mean, obviously a larger coherence D value, okay, means a most important impact for a particular factor that you consider. Okay. So that's like the coherence D. Okay. So another way to report the effect size is the probability of superiority. Okay. What is probability of superiority? Okay. Okay. Intuitively, okay, the meaning of probability of superiority is defined as the probability that a data point taken at random from one group, okay, has a larger value than another value taken at random from the second group. Okay, so you just randomly take value from two groups, okay, and then you compare these two values. Okay, so that's the probability of superiority. Okay, but we know this is difficult to calculate. But actually, if you assume the data is distributed as a normal distribution, which is, a lot of time if it's not exactly normal, but it can be approximated by a normal distribution. Okay, if that's the case, we can compute the probability of superiority from coherence D. Okay, using this expression. Okay, in this equation, okay, this is probability of superiority. Okay, this delta, okay, is the coherence D. Okay, and this phi, okay, is the cumulative normal distribution. Okay, it's another distribution that is well known. Okay, if you know normal distribution, the cumulative normal distribution is related to normal distribution, but it's like it's represented by like an integral of a normal distribution basically. Okay, so this I already explained what the data is. Okay, so you can see if you have the delta, you can get the probability of superiority from this formula. Of course, with the understanding that the model, okay, or the distribution is normal. Okay, this is assumption. Okay, so we can compute a point estimate of the probability of superiority. Okay, or we can compute the whole posterior distribution of the values. So this is one way to compute just a single estimate of the probability of superiority. But if you want, we can also use we can also compute the whole posterior, the distribution of the probability of superiority. Okay, so if we are okay with the normality assumptions, this normality assumption, as I said, okay, it works a lot of time, because a lot of models can be approximated by normal distribution. Okay, so we can use this formula to get the probability of superiority from coherence D. Okay, otherwise, as we have samples from the posterior, we can also direct compute the coherence D. Okay, so of course you don't compute this thing by hand. You compute this thing by the program. Okay, so it's not that difficult. Okay, just use like the program to do the job. Okay, so here, okay, we are, looking at another example. So this example is sort of interesting. Okay, because in Taiwan, when you go to a restaurant, like the tipping is at the fixed rate, right? Either the restaurant does not take tip, okay, you just pay for whatever you order, okay, or okay, if the restaurant take tip, okay, they will just add that value, add that percentage directly in your bill, right? Okay, for example, if you spend like $100 for your meal, okay, you will see the bill may be 110, right? In there, okay, the $10 represent the tips, right? Okay, so that's like the situation in Taiwan, but this is not the case in U.S. Okay, in U.S. it's customary to give tips, okay, but the tip, okay, the amount of tips depends on the quality of the service. Okay, so if you like the service this restaurant provide, okay, you can give like more tips. Okay, if you don't like the service, okay, you can even like give like 0 tip, which represent you don't like their service. Okay, you just, this is an indirect way to tell the restaurant that their service sucks. Okay, but in Taiwan, like, we don't have this system. Okay, so but anyway, like of course, like in US, like the tipping percentage, if you get like when I was in US a long time ago, like the percentage of the tipping, okay, for example, for lunch is normally 10%. Okay, I mean, if the service is reasonable, okay, reasonable is normally 10%, okay, or close to 10%. I mean, if it's dinner, then it's normally like 15%. I'm talking about like in general. I'm not saying like this is like a written rule, but I'm saying like okay, if you feel like okay, the service is reasonable, it's okay, and you know, as I said, because tipping is sort of mandatory in U.S., so you have to tip. So you just calculate like this amount as your tips. Okay, but obviously, like you know, this study is interesting. Okay, because this data was reported, okay, first time by these 2 researchers in 1995 in Practical Data Analysis, Case Study in Business Statistics. This is a journal paper, actually. Okay, so in this paper, they want to study the effect of the day of the week on the amount of tips at the restaurant. Okay, so basically, like they observe like you know, on different days if the tipping behavior will change or not. Okay, so of course, in this case, the different groups will be different day, okay, of the week, different days of the week. Okay, so there's no control group or treatment group because, well, we just break the result into different number of days, different days. So if we wish, we can arbitrarily establish one day, okay, for example, like Thursday as the reference or control, okay, but well, we don't have to, okay? So this is the data set, okay? I mean, the CSV, oh, by the way, I told you guys, like, all the program as well as the data set of this textbook can be downloaded, right? Okay, I mean, you can just check out, like, the book, and I think in the preface or somewhere, it tell you, like, where to download all the data, okay? So, yeah. So this is the data, okay, tips.csv. So you read, okay, you just, got this data and store in the tips, okay? And then tips.tail just output the last few entries of this data set, and it looks something like this. Okay, the last 5 entries look like this. Okay, what we are interested in are this one, the tip, and the day. Just these 2 columns. The other the other columns do not. I mean, doesn't matter. Okay, the other columns do not matter. Okay, I mean, of course, if you study other type of behavior, okay, related to tips, you may want to check out the other columns. But for this, for the purpose of our, what we are doing now, so we only care about the tip and the day, okay. And interestingly, they only collect this data from 4 days, okay, of the week: Thursday, Saturday, Friday, Saturday, and Sunday, okay. So you can see there are only 4 groups, okay. If you just use the just output this 4 group of the data, okay, by using the day and the tip, okay, and you can generate what we call variant plot. Okay, it looks like this. And by the way, the reason why the study only care about these 4 days, obviously, is because Thursday is a typical weekdays, right? It's a typical weekdays. I mean, just like a Monday, Tuesday, and Wednesday. Okay, Thursday is just one typical like weekdays. I mean, you don't have to collect every weekday. Okay, just Thursday should be enough. And the Friday happened to be the, what should I say, like in between the weekday and the weekend, right? So something will be different. Okay, it must be different, like on Friday. Saturday, Saturday sits completely inside the weekend, right? And for Sunday, okay, because Monday is a weekday, okay, so a lot of people do not go out for dinner, okay, so the tipping pattern will change, okay, on Sunday. The tipping pattern between Saturday and the Sunday, a lot of times different. Okay, so the reason to collect just these 4, the tipping pattern, or just for these 4 days, there's a reason behind that. Okay, you don't have to draw the variant plot, obviously. I mean, but this is just one way to represent the data. Okay, so now, okay, we have, we can simplify things, okay? We can create 3 variables. The y variable, okay? Y variable represents the tips. okay, and the IDX represent the categorical variable, okay, which encode the days with numbers. For example, okay, this IDX, okay, is 0, 1, 2, 3, okay, which represent Thursday, Friday, Saturday, and Sunday, okay, respectively. Okay, so 0 represent Thursday, 1 represent Friday, and so on. Okay, so finally the group variable, okay, with the number of groups. Okay, so we have these three things. Okay, so yeah, I mean, here we just define these features. Okay, that's it. Okay, and then okay, we are going to create a model for this problem. Okay, this model is almost identical to the model G. What is model G, by the way? It is a model we use for that chemical shift. Remember? I mean the first one. Okay, not the one before the student's T distribution. Okay, so it looks yeah, it looks like you know, we have like you know, normal distribution. Okay, which I mean y is distributed as a normal distribution, and because it's normal distribution, so we have like mu and sigma, right? So so mu, okay, you know, is distributed as a normal distribution, okay, and with standard deviation 10. Sigma is distributed as half normal, okay, with standard deviation 10. So here, okay, it's to be honest, I mean, there are still something that's different, okay, in this model, because if you look at the model G, you remember that for mu we use not normal distribution. We use uniform distribution. Okay, in between 40 and 70, if I remember correctly, right? But no, we use normal distribution, okay, to represent the prior of mu, okay, and we set its mu and the standard deviation as a 0 and a 10, okay. So we have changed something here, okay, and then the other part, I mean, are kind of similar, okay, and then we just generate the trace, okay. We call this model like comparing groups, and the trace is CG, okay, comparing group, okay, previous comparing group. So we generate like 5,000 samples. So this sample is larger, okay, 5 times larger than the samples that we collect previously, okay, and then we plot the trace, okay. So the result looks like this. Okay, the posterior of mu, okay. Keep in mind, we have 4 groups, right? So we have 4 mu's, okay. Mu 0, mu 1, mu 2, and mu 3. Mu 0 represent the mu for the Thursday tips, okay. Mu 1 represent the mean of like Friday tips, okay, and so on, okay. So you can see they are slightly different, right? It looks like Sunday's tip is higher, right? Sunday's tip is higher. So, but anyway, and this is sigma, okay. Again, we have 4 different sigma: sigma 0, sigma 1, sigma 2, and sigma 3. Okay, and they obviously have, you know, distributed quite differently. Okay, and then, okay, the most important thing is, generating this is just like the previous one. I mean, we have these 4 groups. The only difference, I mean, compared with the previous example is now we have 4 groups. So we generate the mu and sigma for these 4 groups. Okay, but the more important thing is that we want to plot the differences. Okay, the differences. So this code is just a way of plotting the difference without repeating the comparison. Okay, so instead of plotting the all against all matrix, we just plot the upper triangle portion. What do we mean? Okay, so we want to see, because for 4 groups, let's say group 1, group 2, group 3, group 4. Sorry, we have group 0, group 1, 2. Group 0, group 1, group 2, group 3, right? And you could do the comparison. If it's like, if you consider all by all against all, then it's a 4 times 4, right? So you have like a 16 blanks, okay, like 16 pairs to compare. But you know, like out of them, like you don't compare with yourself, right? So the diagonal is gone. Diagonal is gone. You don't compare like one model against itself, so you don't do that. And this metric obviously is symmetric, so you don't need to if you have this, you don't need this, right? So you only need like the top triangle. Okay, that's what we meant. Okay. So this piece of code, just do this, okay? I will not go into the detail like line by line, but the result is something like this. So the first one is mu0 minus mu1. The second one is mu0 minus mu2. The third one is mu0 minus mu3. And then mu1 minus mu2. Mu1 minus mu3. And then mu2 minus mu3. Okay, so we have 6. Okay, that's good enough, because originally we have 16, right? Getting rid of the the diagonal, we have 12. Okay, and we only need half of them, so we have 6. Okay, so we are able to output like the difference of the mean. Okay, in terms of posterior distribution. Okay, and then in here we also mark the reference value, which is 0, because when we subtract one mean from another, if the difference is 0, that means they are similar, right? There's not much difference between the 2 groups, right? So first we can observe, like if this reference value is inside their 94% HPD, okay? So you can see that, okay? Well, out of these 6 results, the only one that, the 0 does not, this zero reference value does not fall inside the 94% HPD is this one, right? What is this one? This was mu0 minus mu3. So Thursday and Sunday, okay, these 2 groups are the most different one. Okay, you can probably say that. Okay, This is based on, okay, this is based on this one, posterior plot with a reference value. I already show you, okay, with a reference value 0, okay, you can claim that like the Thursday's tip is is lower than the Sunday's tip. Okay. So, so the difference in tips between Thursday and Sunday. So for all the other example, we cannot rule out a difference of 0, okay? Because the difference the 0 is still inside the 94% PD. So even for that case, okay, it's an average difference of $0.5, large enough, okay? So is that difference enough to accept working on Sunday, missing the opportunity to spend time with family, okay? Is that difference enough to justify averaging the tip over the 4 days and giving every waitress and waiter the same amount of tips money, okay? Sometimes this is the practice of the restaurant, okay? It depends on the restaurant. Some restaurant, okay, for example, like if a customer give tip to a particular attendant, okay, then that attendant, okay, either waiter or waitress, will just collect that money at the end of the day, okay, from the restaurant, okay. But sometimes, okay, like the restaurant will collect all the tips and distribute evenly to all the waiter or waitresses, okay. It's just because like some restaurant, like the business model, okay, for the waiter waitress are more kind of like a cooperative. They work cooperatively, and so it's difficult to tell. Like this service is just this service. I mean, comes from a particular waiter or waitress. Okay, sometimes. Okay, so this is like it depends on how the restaurant like decide like this policy. Okay. Or, okay, those type of questions, okay, cannot be answered by statistics. They can only be informed by statistics. So the statistical result okay, help maybe like people to make decision, but the decision is still made by people, not by the this statistics result. Okay. And then, okay, the interesting part is here, okay? The next topic, okay, this topic is much more interesting, okay? It's a hierarchical model, okay? Suppose we want to analyze the quality of water in a city, okay? We take samples by dividing the city into neighborhoods. So we may think we have two options to analyze this data. The first one is we study each neighborhood separately, okay? The second one is we pool all the data together and estimate the water quality of the city as a single group. Because now we understand the group, right? Okay, but a lot of, this is just one example, but a lot of time, okay, the problem has a hierarchical nature. Okay, so this is one example. Obviously, for example, like if I consider student performance, okay, because like in our department, like for undergraduate student performance, like in our department we have 2 classes, right? For each year we have 2 classes. And so we can also consider, okay, the performance of students in each classes, or we can consider the student performance as a whole, right? So a lot of problem has this hierarchical architecture. Or let me use another example. Okay, if you like baseball, right? I mean, in Taiwan, because we just lost the game. Yeah, probably not a good idea to use this example. Okay, NBA, for example, NBA, because NBA is still like very hot recently, right? Because it's close to the final moment to decide like which team will get into like playoff, right? So if you want to consider NBA team, okay, for example, in a particular position, for example, like because everybody like Jeremy Lin, right? So let's use the point guard as an example, okay? Because every team has point guard, right? Okay, so when you consider point guards, okay, well, you can, because you have different teams, right? Different team has point guard, but of course, if you consider just point guard in one team, that's probably not too many, right? Only one or two players, okay, in one team. But if you consider, for example, point guard like in respective division, okay, NBA is divided into divisions, right? So different division, okay, has a lot of point guards, right? And again, different division, combine form the NBA as a whole, right? So again, you can see there's such a hierarchy, okay, very naturally built in this problem. Okay, a lot of problem has this hierarchical nature. Okay, so it is very common to consider hierarchical models. Okay, so let's continue with this example. This is just one example, and you may be able to see many similar hierarchical example. Okay, so both options. Okay, this study each neighborhood separately, or pull all data together and estimate the water quality, of the whole city. Okay, so both options has the pros and cons. Okay, because the first option allows you to see the differences between different neighborhoods, right? Because you are analyzing the water quality of different neighborhoods. So now you are able to estimate like water quality. And be able to identify, okay, which neighborhood has a better water quality, which neighborhood has a inferior water quality, right? Remember like the group comparison technique that we just discussed, right? So we can do that, right? But okay, on the other hand, okay, because each neighborhood you may only collect a few number of samples, right? So number of samples will be small for each neighborhood, right? Okay, but if you pull all the data together to estimate the water quality of the whole city, you have a larger amount of data set, which allows you to estimate, like do this analysis in a much more confidence. Like for example, like it's just like remember coin flip. If you just collect 4 flips, okay, and another case if you collect 40 flips, even with the same ratio of like a head and tail, one is like this, another one is like this, right? Okay, same thing here. Okay, with more data, it will tell you a much stronger story. Okay, so both options has its pros and cons. Okay, so both are good reasons, but we can do something else. Okay, if you take this one, the first one and second one, okay, so you lost something in between. Either you take first one, you lost some advantage. You take the second one, you lost some other advantage. So what we can do is we can do something else, something in between. We can build a model to estimate the water quality of each neighborhood and at the same time, okay, estimate the quality of the whole city. So this can be done simultaneously. Okay, that's the beauty of the hierarchical model. Actually, like as I said, like most of the questions fall into this category because a lot of questions has this hierarchical nature. Okay, so this type of model is known as hierarchical model or multi-level model. Okay, in terms of the model, it's really not that difficult. Okay, because we model the data using hierarchical structure or one with multiple levels. So, I mean, previously, for example, let me just use any example that we had previously. You see that it's already kind of like a multi-layers, right? Right? We already have 2 layers. So far, the examples we use, I mean, the model has 2 layers, right? It's always like that, right? We could, like, increase this level. That's not a problem. Okay, instead of fixing the parameters of our prior to some constant numbers, we estimate these parameters directly from the data by placing shared prior over them. So this higher level prior is called like a hyperpriors or like a hyperparameters. Okay, they are parameters, hyperparameters. So hyper just means like over. I mean, well, it's just, of course, this is also possible to put priors over the hyperprior. So create as many levels as you like. Okay, so here, okay, we just tell you, okay, we can have not only 2 levels, we can have 3 levels, we can have 4 levels, we can have many levels, as many levels as you want, because each level represents like a layer in your problem, like for example, like water. Okay, this water quality case. Okay, one level can be used to represent like a neighborhood. Another level can be used to represent like a city. Okay, so something like that. So unless the problem really demands more structure, okay, I just told you we can have like as many levels as we want. But at the same time, don't use too many levels because each level you introduce, okay, it's going to complicate the problem or complicate the model, okay? And after you analyze, you have the result, okay? You need to be able to explain the result, okay? And if you introduce too many levels, sometimes it will be very difficult for explanation, okay? So you should just put enough level, or just enough level, okay? You don't just arbitrarily introduce, the number of levels as you want, okay? You just put enough number of levels. So after all, the main idea of building models is to make sense of the data, okay? So thus, models should reflect the structure of the data, okay? Because in the hierarchical nature type of problem, okay, the data you collect actually, has a hidden hierarchy inside that. So your model should also have a hierarchy to reflect that, okay? But not too many levels, okay? Just enough, okay? So, well, I think, we are running out of time. So this water quality example, let's talk about this next time, okay? This is hierarchical model is very, very important, as I said, okay? Which, once we finish this hierarchical model, we'll be able to talk about, like, for example, the the generalized linear model, okay, which is known, okay, for analyzing like a lot of real world problems, okay. So let's take let's stop here, okay. We will continue. I think we will be able to finish this chapter next time, okay, because yeah, we have only like 20 slides. So after we finish this slide, I mean, we will move on to talk about MCMC. Okay, I think the slide has already been uploaded to E class. So please remember to check it out, okay, next time, okay? So I'll see you next week, okay? Okay, thank you.
我想问一下有一个VCAT 那个 tips 那个 problem，就是你的 filter 跟那个